all to the organizers for the opportunity to present the work of our group at this wonderful workshop. So my talk will be more on the physical side of the conference and moreover more on the experimental side. So the talk will be divided into two parts: quantum error mitigation driven by data obtained in classical simulations, and quantum error mitigation driven by analytical computations of evolution equations based on these papers here together with my co-authors. Okay, so what is the general motivation of what we want to do? Basically, if we have a physical system that we want to analyze, we can do this classically, for example, through numerical approaches such as Monte Carlo. However, for many regimes of many interesting physical theories, there can occur some problems. For example, the sign problem, where the Boltzmann factor of the Euclidean path integral becomes complex, and we cannot interpret those as probability weights. So an alternative framework that is instead used is that of quantum computing, which is not affected by this sign problem. However, we then end up with a new problem that current quantum devices are noisy, they're not fault tolerant, so we need an intermediate solution. And the solution is quantum error mitigation, so we somehow try to post-process the data to decrease the error. So as I said, the talk will be divided into two parts. Part one will try to use regimes where we can indeed compute something with classical numerical methods and somehow try to use this information for quantum error mitigation in regimes where classical computations are impossible. And in part two, we will look at methods leveraging the fact that those are physical systems that we model on quantum devices, and they of course obey evolution equations, which we can derive analytically and somehow use this information for quantum error mitigation. So part one, QM driven by classical simulations. What is this specific example of a problem that we want to consider? We want to study phase diagrams of certain physical theories. Normally, as I said, this is done by Monte Carlo. However, this often fails, for example, in Lattice QCD due to the sign problem. And we use quantum computing, and one of the most common approaches used in quantum computing, because quantum computers are noisy, is that of variational algorithms. So for example, if you have your physical state of n qubits, you want to apply some circuit parameterized by a vector of parameters theta, such that basically to find the ground state, you tune those parameters theta such that you end up with a state with the smallest energy. However, this classical optimization problem, which is part of this method, can be challenging, and an alternative method that's been proposed and frequently used is that of adiabatic evolution. So part one, as a small tangent, we will look at the question whether it's possible to find the phase structure of a physical system by adiabatic evolution on a quantum device without the need to actually modify the model. So I'll comment on that later, why the modification part of the model is important. And in the second part, because again, quantum devices are noisy, we will try to mitigate the errors from this first approach by data from classical simulations. Okay, so we want to study the phase diagram of a quantum physical system, and we want to do this by adiabatically preparing states on a quantum device. And the method that we want to use is we want to directly apply the adiabatic theorem. The specific example I will show you is the Schwinger model. So what is the Schwinger model? This is a model that's been introduced by Schwinger. in the 60s, which is essentially quantum electrodynamics in 1+1 dimensions. So psi is our fermion, A is the gauge field, and theta is this topological angle, which, if non-zero, produces sign problem. So yes, we work in the temporal gauge, and the physical states of the theory obey Gauss's law. So what Schwinger discovered is that this theory is periodic in theta with a period of 2 pi and possesses the following phase structure. So for theta equals pi and for some critical mass over coupling roughly a third, there is a second order phase transition point. And for higher masses, there is a first order phase transition line. So those are the two regimes that we'll consider is the first order phase transition regime and the no phase transition regime. Okay, so to study this on a quantum device, we first need to discretize the theory on a lattice, because on the previous slide it wasn't in the continuum. This is commonly done by the Kogut-Susskind approach. Here we choose open boundary conditions. Then we rescale things to make them dimensionless, and we would like, as a specific case, to focus on the zero total charge sector. So we introduce this Lagrange multiplier lambda to enforce the vanishing charge. So sigmas are the usual Pauli operators, and this is the Hamiltonian that we obtain, where L0 is now plays the role of this topological angle theta and is essentially a background electric field. Okay. Yes. Okay, so as I said, there are two regimes that we want to study, the first order phase transition regime and the no phase transition regime. So we will draw the energy levels, the two lowest energy levels of the system with varying background electric field. And for consistency, we'll also track two observables, the particle number and the electric field density in the bulk. So basically, to redraw the diagram from before, we have background electric field, theta over 2 pi. And here we have mass over coupling. So basically what happens, so qualitatively you can think of it as for the first order for the first order phase transition region, for low background electric field, it is energetically more favorable for the system to have no particles in the ground state. And as you tune up the electric field, it becomes more favorable to produce a particle-antiparticle pair that screens the background electric field. And this is exactly what you see here. So particle number 0, and then it jumps up to 2. So in these diagrams, the ground state will always be marked in red, and the first excited state in the dashed line. So in the first order phase transition region, you see that the two bottom energy levels cross, and there's a sharp jump in the particle number, corresponding jump in the, or fall in the background electric field, and there's a first order phase transition. In the no phase transition regime, the two lowest energy levels do not cross. There's a finite non-zero gap, and there is no sudden jump in P and L correspondingly. So the other energy levels that are close are marked in thin black lines. Okay. So the adiabatic theorem, that's what we want to use. One of the initial formulations of the adiabatic theorem developed by Ehrenfest and others in the 1900s. Here are a few first formulations. There were many developments after this. The theorem states that if we consider a quantum system which is parametrized by a time-dependent Hamiltonian and prepared in one of its instantaneous eigenstates, the theorem states that the system will remain in that state if the Hamiltonian is varied sufficiently slowly, and if there is a non-zero gap between the state that we evolve and the rest of the spectrum. So essentially, we can understand adiabaticity for this version of the adiabatic theorem in the following way, that the change in the energy of the system over the time scale of the dynamics of the system must be much smaller than the gap. And knowing that the time scale of the dynamics of the system is governed by the inverse gap, we can introduce this non-adiabaticity parameter epsilon. And one of the beautiful methods that we compare our method to uses this version of the adiabatic theorem. So what the authors in this paper consider is the isotropic XY model, so given by this Hamiltonian in black, which has the following phase structure given by the dashed lines. So you see there are phase transitions here. So to find these phase transition points, what they do is they introduce this extra field in the extra direction x, which breaks this corresponding symmetry such that they avoid this crossing. And what they essentially do is they do the adiabatic evolution over the field Bz for various values of Bx. They know that there is a jump in magnetization, which is the order parameter. They identify the critical value by the midpoint of that jump, and they repeat those steps for multiple values of Bx and extrapolate the critical value for Bx going to 0, thereby extrapolating and recovering these phase transition points. So of course this is good if there are many level crossings in the system. However, a priori there's of course an assumption and a knowledge that there are phase transitions, and this method cannot determine the order of the phase transition. So what happens if there are phase transitions? If there is a level crossing, what happens to the adiabatic theorem? So in fact, this version of the adiabatic theorem was developed almost 100 years ago by Born and Fock. And the statement is the following: let E alpha be an energy level, E a unit of energy, C a dimensionless constant, and tau the rescaled time. And if each difference of distinct energy levels has a finite number of zeros of maximally the rth order, and in the vicinity of each 0 point tau naught this inequality holds, then the theorem states that the transition probability to jump to a different level from which we started evolving is bounded from above by this expression. So qualitatively what this means is that if we have a level crossing of low order, say linear like this, then there is a low probability to jump to a different level. However, if the crossing is very smooth, say something like this, then we need a longer time to evolve. So the main point that I want to stress is that the condition of a gap for the adiabatic theorem is not a necessary condition. So this is the version of the adiabatic theorem that we use. Yes, so in the example of the Schwinger model, we take this background electric field L0 as our adiabatic parameter. We take a linear ramp, for example, and essentially what we do is we evolve the lowest energy states, increasing time t iteration after iteration, and see that our lines converge. And after the difference to the previous iteration with the previous t defined by some user bound, so if the error is smaller than some user defined bound error b with this evolution of the lines from iteration to iteration, we stop. We of course operate under the assumption that if the error goes to 0, we assume that t is sufficiently large, so we're not stuck in some local minimum. And if we test this, so each row so these diagrams are for the top region of the phase diagram where there's a first order phase transition, and each row corresponds to a different total evolution time, increasing downwards. So on the left, we see the probability to stay in the ground state. So after the phase transition, it drops. So we stay on the same level, energy level. So we stay basically on this line here. And the same happens if we start evolving with the first excited state at minimal L0. We indeed also stay on this energy level. This is shown exactly here, and the observables particle number and electric field density in the bulk stay the same. Now, if we look at the no phase transition region, again, time increases from top to bottom. For a low time, we see that, okay, we were a bit too fast and the lines cross. And as we start increasing the total evolution time, we see that the energy levels indeed approach the exact diagonalization results shown here in black. So we do recover the phase structure in both regimes, in the first order phase transition region and the no phase transition region. Okay, so wonderful. So we found the phase diagram by adiabatic evolution of states. Now to the actual main task, we want to perform quantum error mitigation on an actual quantum device. Okay, and so the insight, as I've said before, is that certain parameter regions of the theory are accessible by classical computations, where the computational cost does not become exponential. And the error mitigation method that we want to adapt is one developed by my co-authors and colleagues previously. Again, we consider it on the example of the Schwinger model. And the two main questions that we want to ask are basically, how do we adapt this method for adiabatic evolution? I will go over the details in a second. And the second question is, does the knowledge of error mitigation obtained in one phase of the model transfer to a different phase? Okay. So this Grec method is inspired by zero noise extrapolation and probabilistic error cancellation. I will comment on zero noise extrapolation a bit later, as that will be more central to the second part of the talk. So the general idea is as follows. We have, imagine you have a parameter of your theory, call it lambda, and you have some observable A. So call it A of lambda. And for example, you want to measure, I don't know, for the Ising model, the magnetization in the ground state. And let's say there's a certain region of your parameter where the computations are available. You can perform the computations classically, noiseless, and on a noisy quantum device. And the second region where the computations can only be performed in the, on a quantum device. So basically the idea is that you measure the observable in both regimes. And for the, okay, so say you have the measurement of the observable on the classical part. What you then do is for on the quantum device, you on purpose add noise to the circuit that you have and produce noisy lines, some noisy measurements with some error. And the idea is to find a linear combination of those lines that reproduce the classical results. So you learn in this learning region the coefficients of those lines. What you then do is then you extrapolate to the quantum regime. So of course you measure the same observable with the same parameterized circuits in the only quantum regime, and you extrapolate and infer the error mitigated result. So this is exactly what is shown here. You can perform this for different regions. So for example, you train here, you select the best combination of the lines here, and then you extrapolate to the rest, or the same with the blue region, you train here, validate here, and extrapolate. And those two correspond exactly to the green points and the orange points. So you see that indeed the ideal result is recovered very well. And this is a comparison to a different mitigation method known in the literature called zero noise extrapolation. Maybe let me briefly sketch it here. So the idea of the zero noise extrapolation method is that, again, say you have your state of n qubits, and you apply some gate u, and this has some noise. So what you try to do is you introduce an inverse operation u dagger, and again an operation u. So in an ideal world, this would be unity. However, on a noisy quantum device, this produces some error. And basically, the idea is that you can perform this for inserting multiple copies of u dagger u. So something of this form where f is odd and is the noise factor. And what you can then do is perform the measurements that you want at different noise levels, at different noise factors. And then you extrapolate to zero noise. So this is exactly the purpose of zero noise extrapolation. OK. Now we want to apply this to the adiabatic evolution in the Schwinger model, as we did before. So the two we again consider the two regimes, subcritical and supercritical mass. And we, for example, in the first order phase transition region, we will assign the learning region to before the phase transition, and the phase transition will lie in the prediction region, such that we can test the fact whether this error mitigation knowledge does indeed transfer across phase transitions. OK, so we choose some error model. These are just the specifications where we take a specific gate and assign it a particular error. And the added noise that we add, we fix it to some particular rotation applied to exactly this rotation. So these are just the specifics of the noise that we add. And essentially, we play the same game as before. However, now, because this is adiabatic evolution, we need to perform it time step by time step. So for example, you see here in red a specific time step. And we learn the coefficient how to get from this point to this point correspondingly, and extrapolate it such that the line, the adiabatic evolved line that we want to mitigate, preferably goes from here to here. So we can do this for the two lowest levels in the no phase transition region and in the first order phase transition region. And we can see how this performs. So in black is the exact known result. In blue is the original circuit. In green is our added noise. And in red is the error mitigated result. So we do indeed see that the error mitigation works very well, and we recover the exact result. OK. Just as a comparison, let's compare this with zero noise extrapolation, where for each time step, we perform zero noise extrapolation. And again, here in black is the exact result. In red, in colors, green and blue and mixture are the different noise levels. And in red is the zero noise extrapolation. And here, there's slightly more noise. So let us try to quantify this. OK. So there are two metrics that we can use to judge the performance of the methods. First is the computational resources. So how many gates do we actually need to apply? And the important thing is that for Z and E, that the total number of gates that we apply squares quadratically, because for each noise factor, there's this extra unitary folding after each time step. And for our method, this scales linearly. And we, of course, can compare the error. So the original noisy circuit is around here. And zero noise extrapolation we can perform with different number of noise levels, so for 2, 3, 4, and so on lines. We can do the same for our method, and we see that except for the very first point of Z and E, we outperform both in error and in number of gates. Okay, so as a brief outlook to part 1, there are several extensions that one could consider, basically employing the fact that we can add noise of different noise levels and perform essentially the same mitigation schemes. So to summarize part 1, we have seen that it's possible to find the phase structure of a model without the need to modify the model itself, based on the wonderful theorem by Born and Fock from 1928. And we have used this to perform our adiabatic evolution in the Schwinger model. In part 2, we've seen that it is possible to apply this method, Greg, to quantum error mitigation in adiabatic evolution, and the knowledge of the quantum error mitigation indeed transfers across the different phases of the model. So now into part 2, where we introduce a different error mitigation method, leveraging the fact that those are physical systems that we model which obey physical evolution equations. So again, same motivation as before. Quantum computing avoids certain problems that classical computing is not immune from. However, quantum devices nowadays are noisy. And in part 1, we would like to basically augment the zero noise extrapolation method by employing a hierarchy of evolution equations called the BBGKY hierarchy. And in part 2, if there is time, I will share some work in progress where we are developing extensions of these methods. So what is our goal here? Our goal is to study non-equilibrium dynamics of a many-body quantum physical system on a quantum device. And the insight that we have is that the dynamics of these systems is governed by an exponentially large system of coupled ordinary differential equations. So in general, the game that we want to play is we want to reduce our computational cost. And as soon as it's exponential, this is bad. So we want to keep things polynomial if possible. And the method that we would like to use is that we would like to augment the zero noise extrapolation method by inputting, by adding the observation that those are physical systems that obey physical equations of motion. And we would like to include a polynomial subset of this exponentially large hierarchy of equations. So this has been developed in the 1900s by Bogolyubov, Born, Green, Kirkwood, and Yvonne in different works. And again, the example that we want to consider is the Schwinger model. So this is just a sketch, a reminder of zero noise extrapolation. So basically, a brief recap, what we want to do with zero noise extrapolation. We perform measurements at different error noise levels. We extrapolate to 0. In gray, here's the exact result. And our hope is that by injecting this physical knowledge of the system into our minimization procedure, that we somehow come closer to the ideal result. Okay. So we would like to consider a generic quantum spin-half model of n sites, where this is the Hamiltonian we consider. There is an on-site interaction. Again, sigmas are Pauli's acting. So the sigma mu I acts on site I in a direction mu, where mu is xyz. And there is a hopping term. Okay. The observable that, so we define an observable Q as some Pauli string, which is a subsystem of those n sites. And basically, the game that we want to play is we use the wonderful Ehrenfest theorem, where we assume that Q does not explicitly depend on time. And we evaluate this equation for a given observable that we want to mitigate the measurement of. we plug this in, and the Hamiltonian that we have. So as an example calculation, let's plug in the on-site interaction part. And of course, the only commutator here which will be non-zero is the one acting on the same site. And here we can use the standard commutation relations to evaluate this and perform the computation. What is important is that because there is a summation over lambda in nu, there are only 9 times length of our Pauli string Q terms on the right-hand side. So this is polynomial. So things are good so far. Now we can play the same game for the hopping term and evaluate the right-hand side, and we obtain this beautiful equation. So this has been stated in another work in a similar form. So the important thing to notice here is that if we plug in a Pauli string of length n on the left-hand side, what we obtain on the right-hand side is a Pauli string of length 1 unit smaller, of the same length, and of 1 unit larger. So of course, linear combinations of those. So schematically, we can show it like this. And indeed, the right-hand side, again, contains only a polynomial number of terms. So this is very good. So we can indeed use this. So now we have a general formula for this huge exponentially large set of equations which are coupled. So the first question is, how do we use them? And which equations do we use? So for this, again, this is the schematic from the previous slide. And let's say we want to mitigate a particular observable Q. And for this, we can essentially diagrammatically show how the hierarchy looks like. So imagine we have some set of observables that we want to mitigate. And if we plug those into the equation, these connect to some other observables. And if we plug this back into the equation, we get some structure. And we can essentially define the hierarchy by, so starting from some initial set, we can define a hierarchy by this integer hierarchy radius, so how far we explore this cluster of equations. And the goal is to take a polynomial subset and use this to improve our error mitigation scheme. So for going from left to right, we call those downstream, so down. And from right to left, we call these upstream, going up. OK, so for the downstream connections, this is simple to find, which observables we need to use. We just evaluate the equation that we had. And for upstream, so given a Pauli string on the right-hand side, we want to find those candidates which connect to it. So one can derive that the amount of checks that we need to perform is, again, polynomial in n. So again, things are polynomial and good. OK, so what do we do with this knowledge? Let's say we want to mitigate the quantum noisy measurements of a set of observables Q. And we want to use these BVGKY equations. The way we use this is we measure those at different time steps s, and we interpolate them with the Bernstein polynomial, which has wonderful qualities. So this expression is then linear in the measurements, and there is uniformal convergence of these polynomials to the function being fitted with an error inversely proportional to the degree of the polynomial. So as I said before, the idea is to include those equations into the linear less squares minimization problem as constraints. And here the question we want to answer is there a systematic improvement by including more and more equations? OK. So diagrammatically, we have some observable that we measure at different time slices. So the vanilla Z&E zero noise extrapolation would extrapolate to some value, here in dark red. And if we include those equations in the BBGKY equations into the minimization procedure, we obtain some other value. We interpolate with the Bernstein polynomial and obtain a different result. So the main input is that we now, by adding this physical knowledge that it's a time evolution of a system, we basically connect the information that the observable evolves from time step to time step. And we can define some error measure for an error with respect to the exact results of the zero noise extrapolation of the original one and the one augmented by the BBGKY hierarchy. So again, in the example of the Schwinger model, let's consider some observable, say a particle number, which does not commute with the Hamiltonian, so it will evolve in time, and measure it over time. So in red points, you see the individual noisy measurements. As you see, things get quite bad. As time increases, things become very noisy. And if we perform the zero noise extrapolation, we get those dark red points. So the exact result is shown by the dashed gray line. And with the Bernstein polynomial, we are indeed closer to the exact result. And we've performed a scan of this for different parameter values of the model. And on average, we are indeed better with the BBGKY augmented zero noise extrapolation. So this is just an example for a conserved quantity, such as the total charge of the system. And again, on average, we do see an improvement. So now to address the main question, how does the error scale with increasing radius? So here you can see the radius of the hierarchy that we increase. And G over lambda is just the number of equations over the number of unknowns in the system of equations. Of course, as soon as we reach 1, this is the full exponential hierarchy. So indeed, the error should go to 0. So in red, again, is the zero noise extrapolation. And in black is our zero noise extrapolation augmented BBGKY method. So ideally, this would go to 0. However, it doesn't, unfortunately. Why? Because the linear least squares problem that we use always contains this zero noise extrapolation, which prevents the Bernstein polynomial to systematically affect this minimization problem stronger with increasing R. However, we do outperform the standard mitigation method always. OK, so to summarize, we've derived this BBGKY hierarchy. We've developed a new scheme which outperforms the original zero noise extrapolation. However, unfortunately, the advantage of the scheme does not scale with classical computational cost. So since I do have a few minutes, let me share with you the work in progress that we are performing now. So we would like to generalize this analytical this quantum error mitigation using analytically derived equations of motion to imaginary time. So why is this useful? This is often used to find the ground state of the system. So again, this is useful for finding phase structure of the model. And we would like to expand this to larger Hamiltonians. So again, it's the same type of game that we play. The only non-zero commutator will be the one of Pauli strings acting on the same sites. And again, you can expand this, use the commutation-anti-commutation relations, play the same game, just looks more complicated. And we are, in fact, developing a new quantum error mitigation scheme, which is guaranteed to reproduce the exact results with the full hierarchy. So the error mitigation does get better with increased hierarchy radius R. And this is based on sampling configuration paths by the Metropolis Hastings algorithm. yes, so this is just a note on imaginary time evolution. So note that the Ehrenfest theorem now looks for imaginary time somewhat like this, where this now became an anti-commutator and there's a nonlinear part. So the evolution equation looks much different, so the structure of the hierarchy would be very different, and yes, this is definitely interesting to explore. So again, this is used for finding the ground state of the model, of course under the condition that there's an overlap with of the ground state with the initial state from which we evolve. So now the interesting part is that you cannot actually do imaginary time evolution on a quantum device because the gates need to be unitary. So instead what you do is you again go back to the variational algorithms where you try to find some effective evolution operator which mimics this imaginary time evolution by tuning those variational parameters theta in the circuit, and you basically iteratively update this parameter theta step by step, mimicking this imaginary time evolution. Yes, so this is just an example of a type of circuit you could have for this variational imaginary time evolution stuff. So this is my final slide. To summarize, there's always a computational game that we play. We cannot allow our computational resources to be exponential. We would like to always keep them polynomial. Classical methods fail for some regimes of the theories, so we resort to quantum computing. However, modern devices are noisy, so we need quantum error mitigation. And in part one, we've provided an example how we can use regimes where we can compute things classically for quantum error mitigation. And in part two, we've used the knowledge that those are physical systems that we evolve to and use this for quantum error mitigation. With that, I would like to thank you. This is all.
Thank you. Questions?
In your simulation, n is the number of qubits.
Yes.
How n is large?
Oh, it's small. For our systems, it's below 10, so 6, 8, something like that. Yes.
It's just simulation worked for computer, personal computer.
Yes, yes. So the simulations that we run, we can indeed run on a laptop device, yeah.
Yes. I have a lot of questions, but okay. So, why did you choose the Schwinger model? Is it because he has, this gap, and he has a phase transition? Is it because of that? Because we are simpler model than this one, perhaps, that we can simulate. For instance, a Landau Hamiltonian or something which is simpler, or just Dirac field. I don't know, but this one is really particular. Of course, it's QED. Is it because of that you have chosen him? Why this one?
Yes, absolutely, you're right. So because of the phase transition and because of this sign problem, specifically because of the sign problem. So in
other model doesn't have it, you mean?
Yes, so other models do not necessarily have a sign problem, yes. So if you, even in the Schwinger model, if you set theta to 0, things are fine, you can compute everything classically. But in Lattice QCD, you also have the sign problem. So the Schwinger model is kind of a test model to test your error mitigation schemes, to then see, okay, this one works well, we can apply that later for the real stuff for Lattice QCD.
Yes. So at the beginning of your talk, you had a model, an example in which you had the phase transition which was 0.33. And is it the case that it's just a numerical evaluation and we don't know if it could be 1/3, or do you know closed form formula for this 0.33?
I know definitely that it's not 1/3. It's approximately 0.33 something. I don't remember exactly what the number is. But I think it has been derived.
And there is a kind of implicit equation for it, or is it some iterative schemes which allow you to get this value?
Just 1 second, I think you were talking about this.
Yes.
I would have to look it up. I'm sorry, I don't.
And quite often you said, so we do an extrapolation lambda to 0,
Yes.
lambda equals 0. So is it in fact always the case that behind it you have a function which is analytic in lambda and well defined in 0, or it's a conjecture, or do you need to have an analytic continuation? So
I'm sorry, let me understand. By lambda, you mean the zero, the noise level, or?
so you had lambda was, I think, your Lagrangian parameters that you were adding, no? Lagrangian
Multiplier.
You mean okay, I think I understand now. Sorry. You mean this guy here?
Yeah.
Yes. So what was your question?
So you said that you were doing an extrapolation with lambda equals 0 after to get back to another model.
No. So in the particular case that we considered is just to look at the zero charge sector. And to enforce this, we introduce this artificial term, and we take lambda to be huge, such that the other energy levels are pushed very high up in the energy, such that we are, we're isolated in the zero charge sector. That is the only purpose of it.
More questions?
You haven't shown us your U theta. Okay, the unitary that you use for medicating the because over there it's a unitary operator, so you have your Hamiltonian and you exponentiate it, take perhaps discrete step or something like this. What about yours there?
In which?
In your Greek, in the Greek setting.
So there is no variational parameter in the Greg setting.
So what do you use as a gate there for your?
Okay. So it's okay. So what you do is okay. So you take the usual time evolution operator e to the minus iht.
Yeah.
You approximate this with the Baker-Campbell-Hausdorff by
Okay, you blow the thing.
e to the x plus y is approximately e to the x times e to the y for small times.
Okay.
Then you decompose that into gates, and this is your one slice u.
Okay.
And then you stack that on top of each other, and that's it. So in this sense, you're right. Variational methods are sometimes more efficient because the size of the circuit is kept the same, and you're just tuning the parameters.
I see.
In that sense, you do kind of minimize the noise that you input.
Next speaker again.